The surprising part of climate engineering is not the hardware, it is the proof. If you cannot attribute an effect, you cannot govern it, ensure it, or defend it. Start with what already works in 2026. The highest operational maturity is in observation, forecasting, climate services, and climate risk screening. Leaders can already translate climate exposure into procurement and design choices. That is real leverage, because it changes what gets built, where, and to what standard. By contrast, intentional planetary scale intervention remains far less mature, mainly because verification, liability, and cross-border governance are still unresolved. One key finding is that the atmosphere is not a set of independent local knobs. Planetary scale circulation is a coupled, nonlinear system. It includes teleconnections, ocean-atmosphere coupling, and chemistry-climate feedbacks. Push in one place, and the response can show up somewhere else. That is why intervention-grade control is so constrained. You do not just need an engineering delivery system, you need confidence about system-level responses and about who experienced harm and why. A second, counterintuitive insight comes from climate carbon modeling. In 2007, transient simulations showed that geoengineering-style forcing can change more than surface temperature. It can alter carbon cycle trajectories too. That matters for strategy, because many proposals get sold as single metric control. Cool the planet by a certain amount and you are done. These simulations say that is an incomplete claim. If temperature, ocean uptake, biosphere response, and atmospheric carbon move together, then a successful temperature outcome may still be a long-run carbon problem. Decision documents that optimize temperature alone are, in effect, optimizing the wrong objective function. Third, governance can stop deployment before technical debates are settled. Ocean fertilization made that clear in 2009. A proposed field experiment was suspended amid environmental, oversight, and legitimacy concerns. The controversy also drew criticism focused on ecological uncertainty and monitoring adequacy. The lasting lesson is not whether fertilization works. The lesson is that legitimacy can be the binding constraint. If your intervention cannot pass oversight, monitoring, and consent thresholds, it may never reach the point where the science can even learn from it. Now contrast that with the most deployable toolkit class available today. In 2023, climate risk toolkits for infrastructure, public-private partnerships were formalized across several sectors. Renewables toolkits translate climate hazards into project screening, procurement language, design requirements, and risk allocation. Similar toolkits were published for ICT infrastructure, for roads, and for hydropower. This is climate engineering in the practical sense, not changing radiative balance, but changing what assets survive floods, heat, drought, wind, and compound hazards. For capital allocators, this is where climate data becomes enforceable decisions and where resilience stops being an aspiration and becomes a contract term. Once you see that, a pattern emerges. The frontier is not bold intervention first. The frontier is bounded intervention with attribution, reversibility where possible, and lawful authorization. That pushes measurement and modeling into the center. Organizations like NOAA, NASA, Earth Science, the UK Met Office, and the European Centre for Medium-Range Weather Forecasts matter here because they support the observation standards, reanalysis, and climate services that make attribution feasible. Research institutions that build and stress test Earth system models matter too, because they characterize uncertainty instead of hiding it. Attribution is the hard gate. You need to distinguish deliberate forcing effects from internal variability, background climate change, chemistry circulation coupling, and regional teleconnections. That is not an academic point. If a downwind region claims harm, your ability to answer depends on independent measurements, calibrated sensors, and auditable model provenance. Without those, liability becomes political, and politics becomes the control system. International law frames this as a governance problem that comes before deployment. Authorization, transboundary harm, liability, and legitimacy are not later. They are prerequisites. That implies concrete operational requirements. Who can approve a field trial? Who can halt it? What evidence counts? What monitoring is mandatory? How disputes get resolved? And what compensation mechanisms exist when attribution is contested? For the near term, from 2026 to 2050, the most likely expansion is not planetary intervention. It is broader climate risk toolkits, stronger observation networks, better reanalysis, and procurement rules that force adaptation into project finance. More ambitious regional intervention research may be possible later, but only if observation and legal frameworks mature together. Over the long run, even if physics permits sustained radiative management, coordination ceilings, termination rules, and legitimacy risks may dominate the timeline. So the practical takeaway is simple. Fund attribution before intervention, and treat models as governed infrastructure, not persuasive graphics.